So in this video we're going to find the eigenvalues and the associated eigenvectors for a 2 by 2 matrix. So we want to find the eigenvalues and the eigenvectors for the matrix A equals 1, 3, 5, 3. And so what we want to remember is that we want to find a vector x or vectors x such that A times x equals lambda times x. And x will be the eigenvector or eigenvectors, and lambda will be the eigenvalue or eigenvalues. It's possible there will be one or two eigenvalues and eigenvectors for a 2 by 2 matrix. So if we walk through this kind of from scratch, because I think it's good to do it from scratch in the first homework assignment. So we have our matrix A. So it's 1, 3, 5, 3, so no shortcuts, and we're trying to find a vector x such that when we multiply this matrix times x, we get lambda x, where lambda is some scalar that we're hoping to be able to find. And so remember, the process that we went through was that we introduced the 2 by 2 identity matrix in here, so that we had a matrix the same size as matrix A. So 1, 3, 5, 3 times vector x, the eigenvector x. And then we subtracted this mess from both sides right here, so that we got the 0 vector on the right hand side. And when we did the subtraction, we took and factored the x out. So we get 1, 3, 5, 3 minus lambda times the identity matrix for 2 by 2 matrices, and we factor out the x. So if you multiply lambda times the identity matrix, all you're going to get from that is 1, 3, 5, 3. All you're going to get from that, if you do lambda times I, where I is the 2 by 2 identity matrix, and this is times x equaling the 0 vector, you're going to get, when you distribute lambda in, you wind up just getting lambda on the diagonal. So you get lambda, lambda. And then we need to do the subtraction. So when we do the subtraction, we're going to wind up with 1 minus lambda in row 1, column 1 position. 5 minus 0 is just 5. Then we get 3 minus 0 down here, and then we get 3 minus lambda. 3 minus lambda. So we have so we have some matrix times x needing to equal 0. So we need to, what we need to do, remember, this is a homogeneous system. We know that the trivial solution x equals 0 exists. So what we want is infinitely many solutions. So we need this matrix here to not be invertible, and by definition the eigenvectors need to be non-zero vectors. That's by definition. We're after the non-zero vectors or the non-trivial vectors that work for this system of equations here. So what we need to do is find values for lambda that make the determinant singular, or make the matrix singular, and that the determinant is equal to 0, so that the inverse of this matrix doesn't exist. So what we need to find is the determinant, 1 minus lambda, 5, 3, 3 minus lambda. We need to find values for lambda that will guarantee that this determinant is equal to 0. So we know how to calculate the determinant of a 2 by 2 matrix. We take the product of the main diagonal. So we do 1 minus lambda times 3 minus lambda. And then it's minus the product of the other diagonal. So 5 times 3 is 15. And we need to find values for lambda that will make this determinant calculation equal to 0. And then we can simplify things a little bit. So we get 1 times 3 is 1. We get minus 3 times lambda. Minus lambda times 1 is going to be minus 4 lambda. Minus lambda times minus lambda is plus a lambda squared minus the 15. And that needs to equal 0. Again, we're trying to get the determinant to equal to 0 so that the inverse of this matrix doesn't exist, which will guarantee infinitely many non-trivial solutions. So kind of putting this in order and combining like terms, we'll get lambda squared. Let's see, minus 4 lambda here, and then 1 minus 15. Why did I have a 1 there? 1 times 3 is 3 because I can't multiply. 1 times 3 is 3, you fool. And we're going to get 3 minus 15 is minus 12. And this, so notice we have a polynomial in lambda. Lambda squared minus 4 lambda minus 12 is a quadratic. And when you're doing this calculation to find the eigenvalues lambda, you always wind up with a polynomial. Whether it's a 3 by 3 matrix, a 4 by 4 matrix, the degree of the polynomial will change. If you have a 3 by 3 matrix, you expect to get a third degree polynomial possibly. If you have a 4 by 4 matrix, you may get a fourth degree polynomial. The polynomial that you get, that you need to then solve, is called the characteristic polynomial. Characteristic polynomial. So it actually has a name, polynomial. And then what we want to remember is that polynomials always have solutions, but sometimes those solutions might be complex numbers. So it is possible to get complex eigenvalues. We won't in this particular case. So if we can factor this, that's the simplest thing to do. But any way that you can to solve it will work. So you know how to use quadratic formula, solve it by factoring and using the zero product property. You could solve it by completing the square. Any technique that you have in your pocket for solving second degree polynomials. So the factorization of this is going to be lambda, it's going to be minus 6 and lambda plus 2. So if we multiply that out, we should get back this. And from this we can see right away what lambda has to be. Lambda is either going to be equal to 6 right here to get 0, or it's going to be equal to negative 2, which will give us 0 for this factor. So again, what we want to recognize is now we've found the eigenvalues, we need to now find the eigenvectors, and the eigenvectors are these guys right here. X is the eigenvector. This is the eigenvector. So what we need to do is plug in our values for lambda and then solve the system of equations that we have right here. So I'm going to slide over to the next slide to make sure I have plenty of room. So I've replicated right here. I've replicated this equation, and I've typed in the eigenvalues that we just found. So the idea is you need to find, for each eigenvalue, you need to find the eigenvector or vectors that go with it, or the eigenvector that goes with it. So for lambda equal to 6, if I do this one first, all we need to do is go in and plug 6 in for lambda. So doing that here, I get 1 minus 6 is negative 5, 5, 3, 3 minus 6 is negative 3, and this is times the eigenvector needs to equal the 0 vector. So this is just a system of equations. So we could solve it using techniques, for example, that we've already used this semester. So we could do the augmented matrix, or we take the coefficient matrix and augment it with the 0 vector. This would be one way to do it. And what we want to notice is that it's going to be easy to zero out the first row, for example. So we could take, or the second row for that matter, if we took 3/5 of row 1 and added it to row 2, we'd get 3/5 times negative 5 is negative 3 plus 3 is 0. 3/5 times 5 is 3 plus negative 3 is 0. And then we could take negative 1/5 of row 1. So if we did that, we would get negative 1/5 of row 1 would be 1, negative 1, 0. And 3/5 row 1 plus row 2 would zero out all of the second row. And so now this is in reduced row echelon form. So we know that this says x sub 1 minus x sub 2 is equal to 0, or x sub 1 equals x sub 2. And we could let x sub 2 equal r, where r is any real number we want. And if we do that, we see that for an eigenvalue of -6, the eigenvector x, which is just as a column vector, is x sub 1, x sub 2. The eigenvector is going to be the vector, hey, x sub 1 equals x sub 2 equals r. We'll put r in here where r is any real number. And we could factor the r out and go r times 1, 1. So it turns out that we haven't talked about vector spaces yet, but we will in about a week be going over vector spaces. So it turns out that this is a subspace of R2. We're working with a 2 by 2 matrix. It turns out that this is what we call a subspace of R2, and the vector 1, 1 is a basis for the eigenspace. This is called an eigenspace. But we'll fuss more with that later. We won't worry about that now. For now, this is the eigenvector that goes with the eigenvalue 6, has corresponding eigenvector RR, where R is any real number, and factoring the scalar R off, we can put it in the form R times the column vector 1, 1, and this is probably going to be the preferred way to write it. So eigenvalue, eigenvector. Now I have another eigenvalue. I have lambda equals -2, and I need to know what is the eigenvector that goes with this eigenvalue. So again, it's just a matter of plugging the -2 into the matrix here. 1 minus -2 is 3. 5, 3, and 3 minus -2 is going to be 5. So we get this matrix times the eigenvector equals the 0 vector. We need to solve for x, and we can do that with an augmented matrix. This one's going to be super obvious what we need to do with it. So there's our augmented matrix. Clearly the opposite of row 1 plus row 2 will yield zeros across the bottom row. And if we do 1/3 of row 1, we'll have it in reduced row echelon form. We would have 1 5/3, 0 with 0, 0, 0. So this says that 1 x sub 1 plus 5/3 of an x sub 2 is equal to 0. And then I could let x sub 2 equal, I'm going to use a different letter than I used for the first eigenvalue. So I'm going to let x sub 2 equal t, where t is any real number we wish. And if we do that, then we're going to get the eigenvector here, the eigenvector x sub 1, x sub 2, that goes with lambda equals 2 is going to be given by, hey, x sub 1 equals 5/3 of x, whoops, we need to subtract this from both sides. Take this guy right here. I got ahead of myself right here. X sub 1 equals subtract 5/3 of x sub 2 from both sides. So x sub 1 is going to equal -5/3 times t. If I let x sub 2 equal t, I'll replace this x sub 2 with the t. And then I can do x sub 2 just equals t. And that t could be factored off if I wanted to. It would give me a -5/3 and a 1 as my eigenvector that goes with lambda equals -2. There'd be other forms we could, if we didn't want the fractional form here, we could, we could clear this denominator out if we wanted to, be easy enough to do. But we'll fuss with that another time.